In this video, I will show you some examples of solving non-homogeneous second-order differential equations with the method of variation of parameters. This differential equation is y double prime plus y equals tangent of x. We want to find the particular solution and the complementary solution of this differential equation. Remember that the general solution, if we suppose y to be the general solution of this differential equation, is always the sum of complementary solution and the particular solution, which here complementary solution is the solution of the homogeneous differential equation corresponding to this equation. And the corresponding equation is y double prime plus y equals 0. The homogeneous differential equation is the equation that the left side equals 0. So we replace tangent of x with 0. So this is the homogeneous differential equation. And if we can find the solution of this homogeneous differential equation, that's the complementary solution for this differential equation. For solving this homogeneous equation, we write the characteristic equation r squared plus 1 equals 0. If you are not familiar with finding the solution of a homogeneous differential equation, you can watch my videos about finding the solutions of homogeneous second order or higher order differential equations. Now that we have the characteristic equation, we have to find r. r squared equals -1, and from this, if we take a square root, r equals plus minus a square root of -1. Usually we show a square root of -1 with symbol I. So in this case, the characteristic equation has two complex roots. And note that here we can suppose here we have a 0 and the coefficient of I is 1. Remember, when we have complex roots in the form of a plus minus bi, the complementary solution or the solution is e to the ax times by c sub 1 cosine bx plus c2 sine bx. So in this case, which a is 0 and b is 1, y equals to e to the ax, but a here is 0. E to the 0 is 1. So this part is 1 and we don't need to write this part because this is 1. Only we have to write this c1 cosine of 1x because b here is 1. Cosine x plus c2 sine x. So the complementary solution is c1 cosine x plus c2 sine x. Now we are ready to find the particular solution. Always first we have to find the complementary solution. Then we can use the method of variation of parameters to find the particular solution. And note that in this example, we cannot use the method of undetermined coefficients for finding the particular solution. We can use only the method of undetermined coefficients when the right side of the equation is a polynomial or exponential function or sine and cosine, which none of them is here. We have tangent of x. So for finding the particular solution, we can use the method of variation of parameters. The formula that we use in the method of variation of parameters for finding the particular solution is this: -y1 integral of y2 f of x over Wronskian of y1 y2 dx plus y2 integral of y1 f of x over Wronskian of y1 and y2 dx. And note that in this formula, y1 and y2 are the two functions that here we found in the complementary solution. So in this example, y1 and y2 are cosine and sine of x. F of x, here the f of x, the integrals, is the function in the right side of the non-homogeneous differential equation. So in this example, f of x is tangent of x. And the Wronskian of two functions, what is Wronskian of y1 and y2? This equals to this determinant. First, you have to put the two functions here, and the derivative of those functions is the second row, y prime 1 and y prime 2. By finding this determinant, probably you know how to find a determinant like this. But if you don't know, it's so easy. Just multiply this by this. So this equals to y1 times by y prime 2 minus, multiply this by this. So minus y2 times y prime 1. This is how we calculate a 2 by 2 determinant. I think now everything is clear for you in this formula. We know what is y1, y2, f of x, and Wronskian. So let's start our calculation. Always it's better to first find the Wronskian. Here we want to find the Wronskian of these two functions, cosine of x and sine of x. And this equals to, put these two functions in the first row and the derivative of them in the second row. Derivative of cosine is negative sine and derivative of sine is cosine. This equals to multiply cosine by cosine. This is how we find a 2 by 2 determinant. Cosine of x times cosine x is cosine squared x minus, multiply this by this. We get negative sine squared, but here we have a negative. Don't forget this negative. So we have plus sine squared x. Cosine 2 plus sine 2 is 1. So Wronskian of cosine of x and sine of x is 1. The next thing that is always better to do is to calculate these integrals first. And then after you find these integrals, substitute them in the formula for finding the y particular. Let us start with the first integral. Integral of y2 f of x over Wronskian of y1 and y2. y2 is sine x, so integral of sine x times by f of x. F of x here is tangent of x, so times by tangent of x over Wronskian, which is 1 dx. Let me show you how we can find this integral. For finding this integral, we can write tangent of x as sine over cosine. And now if we multiply this function by this function, sine of x times sine of x over cosine x is sine squared x over cosine x dx. But how we can find this integral? If you try to use methods like substitution method or part by part, probably you cannot find this. The easier way that you can find this integral is to use one of the trig identities. Remember, sine squared plus cosine squared is 1. And so, sine squared is 1 minus cosine squared. So here I want to replace this sine squared with 1 minus cosine squared. So this integral equals to integral of 1 minus cosine squared x over cosine x dx. Now, if we separate the terms in numerator by denominator, this integral is 1 over cosine x minus cosine squared over cosine, which if we cancel one cosine from the top with one cosine from the bottom, this equals cosine x dx. Now note that 1 over cosine is secant of x. Reciprocal of cosine is secant. Secant is reciprocal of cosine. And we know that from the formula of integrals, integral of secant is ln of secant of x plus tangent of x. Hopefully you remember this formula. And what is integral of cosine? The integral of cosine of x is sine of x. So finally we have this integral. Integral of sine of x times tangent of x dx is ln of secant of x plus tangent of x minus sine of x. So this integral is ln of sine of x plus tangent of x minus sine of x. Now let's calculate the other integral. Integral of y1 f of x over Wronskian of y1 and y2. Here the y1 is cosine x, f of x is tangent of x, and the Wronskian is 1. Tangent of x is sine over cosine, which if we cancel cosine with cosine, this equals integral of sine of x. Again, note that we have cosine x times tangent. Tangent is sine over cosine. Cancel cosine with cosine, and only sine x remains. Integral of sine of x is negative cosine x. Now that we have the value of these integrals, we can put the values instead of the integrals, and so we can find the particular solution. So the particular solution equals to negative y1 negative cosine x times by this integral. As we see here, this integral equals this ln of sine of x plus tangent of x minus sine of x plus y2, which is sine x, times by the other integral, which is negative cosine x. So let me make this negative sine x cosine x. If we multiply negative cosine x by this in the bracket, negative cosine x times negative sine x is sine x cosine x, and here we have a negative sine x cosine x. So it's better to write your answer as y particular equals negative cosine x times by ln of sine x plus. Again, note that if we multiply this in the bracket, we have cosine x, sine x, and minus sine x cosine x. They cancel each other, so only this remains from the particular solution. So this is the particular solution, which if we add to the complementary solution, we can have the general solution for the differential equation. I hope by watching this video you get a bit familiar with the method of variation of parameters. In the next videos, I will show you more examples with this method.